Welcome to tonight's lecture. So still under vibrations and waves. So after finishing vibrations, we're going to start waves. The formulas are almost the same, so we're not going to take a lot of time on waves. Yeah, so we're going to do the tutorial sheet immediately after doing the two topics, vibrations and waves. Then today, we're going to look at the period frequency and the angular frequency. All right, so this is just what we're going to look at. So let's look at the period, the frequency, and the angular frequency. So start first by looking at the period and how to derive the period. So in deriving the period, we have to look at this diagram here. We have to consider this diagram. So when you take a look at this diagram, this is just a ball. We have a ball which has been it has been put at a fixed point like that, and then this is a ball there. So we also have a lamp this side. So we have a torch this side. It's able to give light. So it's giving us light like this. Yeah, so we have a lamp this side. So now this ball is rotating anti-clockwise like that. So then apart from that, we have a table down. We have a table down. This table is just there to give us the shadow. So as this ball is rotating, the shadow down here is not going to be, when you look at it from this point, from this view, when you look at it from this view, you discover that this shadow that is going to be cast on this table here, this is going to look as if it will not be, in short, you not look at it as something that is rotating. It's going to be looking at, rather it's going to be looking like something that is just going to the left and to the right, to be going to and from this point. So this point here is the one that we're going to call the equilibrium point. Remember on the screen, we had a equilibrium point. We had something like this, a spring connected to a certain wall. Then at this point where a spring cannot either go to the right or to the left, it's called at the equilibrium point. If it has a mass somewhere there, it's called at the equilibrium point. And then when you compress it, it will go to the left, meaning the velocity this side is negative. And then when you stretch it to the right like this side, we're going to have a positive velocity. And at maximum stretch, the distance that the spring moves is equal to the amplitude of the spring. So at maximum stretch, we know to say the potential energy there is just given by K. That was, I think, K, it should be KX, it should be half. All right, we'll look at it, but it should be half KA squared. We don't use X. Yeah, we don't use X. We use A instead of X. Yeah, it's supposed to be half KA squared. So you should take note of all these. You have to make sure that you know this concept of a spring. So now let's get back to this. So I was saying, when this ball is rotating like this, when you're looking at it on this view, which is the front view, when you look at it using the front view, you are going to discover that this will be seen as something that is rotating. But when you look at it, when you look at the shadow on the table here, you just look at something that is moving this side. After going this side, it goes back this side. From there, it goes this side again. From there, it goes that side. That's how it's going to be looking. To be like this, to be looking like this, going this side. That's what you're going to looking. That's what you'll be looking at it. That's how it's going to be appearing, in short. Okay, but when you look at it from this point of view, which is the front view, you see something that is rotating like that. So now connecting these 2 points, the one that is viewed as a shadow there, and the one that is just viewed normally there, we have to understand that the velocity of anything that is the velocity of just anything is given by the the distance, rather the displacement, which is d over. So in this case, we can call that as in this place we can call that as 2a, but because we know that the distance from there to there is a, so we can call that as 2a, rather not really 2a, but if we consider the circumference of the circle, so we're going to have d over t. We know that the velocity of anything is given by the displacement over the time taken to cover that displacement or the distance. So this velocity, in this case, this ball is moving around. So when it's moving around, we know to say the distance around the circle is given by the circumference, and the circumference of the circle is simply just 2 pi r. And then in this case, the value of r is simply just equivalent to a. So this can be written as 2 pi a. So the distance on top there can be written as 2 pi a, and then over the time. So the time that this ball is taking to move from this point to go around, to move around this circle, in short, the time it's taking to move around this circle is just equivalent to the period of this given to the period of this same ball, or to the period of this shadow down there. So this is how you write the velocity in terms of the period. Yeah. So from there, we can now make the period as the subject of the formula. We can make the period as the subject of the formula by trying to derive the formula for the period. So period is simply just going to be given by when you cross multiply this. So in short, the formula is V is equal to 2 pi a over t. So when you cross multiply there, the period will just be 2 pi a over the velocity. Yeah, so this is the formula for period. This is the simplest formula for period that we're going to look at. So using this same formula, you can also derive the formula for frequency. We know that the frequency is just 1 over period. So when you put this t down there, we're going to have the frequency is equal to 1 over the period will be 2 pi a, and then everything divided by v. So I mean the frequency can also be written as v over 2 pi a. So this a is simply just the radius of this circle, or the distance that this ball is moving from this point to that point. Or if you want, you can call this as the amplitude when you are observing this as a spring. If this is a spring, you can call this as the amplitude. Why are we calling it the amplitude? We know that the distance this ball is moving to the right cannot exceed, rather the shadow of this ball, the distance the shadow of this ball is moving to the right cannot exceed this point. So meaning this is the maximum displacement it can move. So the maximum displacement a spring can move either to the right or to the left is called the amplitude. You remember we discussed these terms when we're just introducing harmonic motions. Okay. So let's look at these formulas now. So I've explained all these notes, and I've explained where we get the velocity, and then from the velocity we get the formula for the period. So now imagine that the ball only moves from this point P to Q, if it only moves a quarter of this whole circumference. So if the ball moves from P to Q, which is the quarter of the whole revolution, yeah, the motion of the shadow is equivalent to the horizontal motion of the object. So the motion of the shadow is going to be equivalent to just the horizontal motion of the object. Yeah. So when this point moves from this point, to that point. So this distance from there to there, I explained this. This distance from there to there will just be equivalent to the motion of, so the motion of the shadow, in short, or the distance moved by the shadow will just be equivalent to the motion, or rather to the amplitude, in short. So the value of x, which is the displacement there, will just be equivalent to the amplitude if we're talking about the spring. So the shadow down there is representing the spring, and then this one going round is representing the circular motion. Yeah, the circular motion of the ball. So we want to get the relationship between a spring or anything that is in a that is in a simple harmonic motion and the uniform circular motion. In short, we're trying to get the relationship between the two, the simple harmonic motion and the uniform circular motion. So when we use the conservation of energy formula, we know to say at this point, at maximum displacement, if we're dealing with a spring or anything that is anything that is undergoing simple harmonic motion, at the maximum displacement, meaning the value of x becomes a. Now at that point, we only have one type of energy at maximum. We don't have the kinetic energy there. So we only have one type of energy, and that type of energy is the potential energy. And then the potential energy for a spring is given by half k a squared. This is the potential energy of a spring. And then at this point, which is point Q, we have the kinetic energy, because at this point, when this shadow is coming this side, this is where we have the maximum kinetic energy. When this is moving up, the shadow will be going this side. So now when it reaches at this point, the ball is not going to be, the shadow of the ball is not going to be, it's not going to stop moving. It will still be in motion. And according to physics, we consider that point at equilibrium when the ball is coming from the maximum displacement. At equilibrium point, that's where we get the maximum kinetic energy. Yeah, that's why we get the maximum kinetic energy. So at this point, which is point Q, we're going to have the maximum kinetic energy. And then the kinetic energy of the ball at that point will simply just be given by half mv squared. We know the formula for kinetic energy. Yeah, so it will just be given by half mv squared. Now, using the conservation of energy, we know to say the energy, rather the mechanical energy of this same whole process is going to be equal to 0 for conservation of energy. Hence, we'll have the mechanical energy. The mechanical energy will just be the combination of all the energies that we have. We know that the shadow here doesn't have the friction. This is just a shadow. Yeah, so we don't have the friction. We don't have all those. So we consider all those, what do we call them? We represent them by W. All those, I've forgotten the name that is used for these types of, or non-conservative energies. Yeah, all those non-conservative energies, we consider them to be 0. So we're going to consider that this has no friction. This whole process does not have any irreversibilities. Yeah, so when we use the conservation of energy, we're going to say the potential energy, we're going to say E is equal to just the two energies that we're able to put into consideration, which is the kinetic energy, then plus the potential energy. And then when we equate this to 0, we're going to have, so when we equate this to 0, we're going to have this, so we can plug the formulas in the expression. But remember, we're not just having kinetic energy, we're going to have the change, because the kinetic energy is changing. At this point, we don't have kinetic energy, it's equal to 0. And then at this other point there, at equilibrium, the kinetic energy is maximum. At this point, again, the kinetic energy is 0. This point, the potential energy is maximum. Even at this point, the potential energy is maximum, but the potential energy at this point, at the point of equilibrium, is equivalent to 0. So when you do the kinetic energy final minus the kinetic energy initial, you also do the potential energy final minus the potential energy initial, you discover that one of these two energies will have a negative. One of these two energies will have a negative. Hence, you have something like this. You have Ke, which is the kinetic energy, is equal to the potential energy. So when you have this, it's easier now for you to replace. So the formula for kinetic energy, for potential energy, is half Ka squared. So we can put half Ka squared this side, and then we have half mv squared this side, half mv squared this side. So now here we can make any of the things that we want. Of course, half and half there will cancel. So just remain with mv squared. We just remain with mv squared is equal to Ka squared. So from here we can derive the formula for the velocity of a particle that is going that is undergoing both harmonic motion and uniform circular motion. So we can simply get the velocity of this, which is just going to be so I said mv squared. Mv squared is equal to Ka squared. So we can make v the subject. So v squared is equal to K over m a squared. So when we square root both sides there, we're going to have, of course, this will have plus or minus. So the value of v will be the square root of K over m. Then this K squared, the square root of K squared will just give you the square root of a squared will just give you a. So this can be simplified or written as a root K over m. So this is the formula. Of course, it's supposed to have plus or minus. This is the formula for the velocity. So the velocity is negative at this point when the ball, when the shadow of the ball is going to the negative. And the velocity is positive when it's going to the positive side of the equal of the equilibrium point. Yeah, so let's now look at what I was talking about. So these notes have explained everything there. So this is what I was actually talking about. Then from there, that's where we get this formula now. So for me, I just made V the subject of the formula. Yeah, so I made V the subject of the formula. After making V the subject of the formula, we had, so making V the subject of the formula, you're going to have, V is equal to the square root of, this will be, okay, did I do the right thing? Let's repeat the same procedure using this formula. So we have this half and that half being cancelled, and then we make V the subject. So we have mv squared is equal to Ka squared. So from there, we make V the subject. So we divide by m. Okay, so we're going to have V squared is equal to, then we have K over m, and then a squared. So we find the square root of both sides. Then this will have plus or minus. So the V will be equal to the root plus or minus the root of K over m times a. So this is correct. So now, if you want to find the ratio of a over v, or if not that, if you want to make a the subject, I'm sure some of you are looking at what is in the, under the square root to say, how come the m according to them is on top, my m is down there. It's because the value of, v is down there, my v is on top there. So if I'm to make the ratio here, my a is going to be down. So meaning my ratio will be v over a, which will just be plus or minus the root of, just be plus or minus the root of K over m. So once I switch this, I flip this, the a goes up, the v comes down. Even what is under the root there should change. So meaning if I say a over v, this is also supposed to change. this other side also supposed to change. This should become m over k. So that's what it means there. And then from there, we can now, yeah, so from there, we can now get also the formula for the period. You can get the formula for the period. Yeah, so you can get the formula for the period. Remember, let me just take you back to these two formulas. The period we made, we found the period to be T is equal to 2 pi A over V. So 2 pi A over V, that was the period. So now we have 2 pi A. Let me just write it here. Period is equal to 2 pi A over V. So while there's the amplitude, while there's this A over V, we can just replace with that part. So we can have 2 pi. Then while there's A over V, we just put the root of M over K. So we put the root of M over K. So these formulas I'm showing you, they are very important. They are the ones that will solve the tutorial sheet. So we make sure that you know them. So I have 2 pi M over K. That's the formula for the period in terms of M and K, in terms of the mass and the spring constant. So what this means is that if what this means is that if the spring has a higher spring constant, if the spring has the higher spring constant or a very big spring constant, it means that it's going to have a small period, meaning it will have a small period. In short, it do not take a lot of time to finish the whole revolution or the whole cycle. In short, understand as we proceed. So this is the period this is the period in terms of the mass and the spring constant. So from there, we can also derive the other formula for the frequency. So the frequency, we know that frequency is given by 1 over the period. So if the period of, if the formula for the period is that, means that we're going to have 1 over 2 pi, and then everything divided by M over K. So when we simplify this, we'll have something like 1 over 2 pi. And of course, there you have the square root of, there we have the square root of K over M. So even this, when we take this on top of, we bring it this side, the M and K should switch. The M and K should switch there. So you have K over M. So make sure when you're writing, these are the simple mistakes that a lot of people make. When you're finding the velocity, what is the formula for velocity? Okay, when you're finding the period, it's M over K under the square root. Then when you're finding the frequency, what is under the root here will flip. They are going to switch. The K will become on top. The K will come on top, and then the M will go down. That's what I'm trying to talk about. So be careful with this part. This is where a lot of people make mistakes. For frequency, it's 1 over 2 pi times the root of K over M. For period, it's 2 pi times the root of M over K. Look at the difference there. Very important. Okay, so from there, we can now proceed and look at the angular, which is the last part. We look at the angular frequency. So, okay. So the angular frequency, we know to say the angular velocity of, let me just use this same page. The angular velocity of any particle that is undergoing harmonic motion, from that example that we discussed, or anything that is undergoing harmonic motion is I mean, that is anything that is going, rather that is undergoing circular motion, not harmonic motion, is simply just given by 2 pi f. So 2 pi f is the angular velocity of any particle that is going, that is undergoing circular motion. So when you combine this with the formula for the frequency, we know that the frequency, according to what we just recently derived, the frequency is given by, so the frequency is given by 1 over 2 pi. This is what we just discussed, 1 over 2 pi, and then root k over m. This was the frequency. So the frequency is given by this formula, meaning the angular frequency, the angular frequency will now be equal to the angular frequency now be equal to, just replace f by that, which is okay, let me just put in brackets, 1 over 2 pi times the root of k over m. So from there we have this 2 pi and that 2 pi will cancel. So when those two cancel, we'll remain with, so when those two cancel, we're just going to remain with the root of k over m. So this is going to be the formula for the angular frequency. So the angular frequency, which is represented by W, will simply just be equal to k over m. All right, so this is all for tonight. So as I said, I've not been putting examples in the slides because I just want us to come and do everything together in a tutorial sheet. Yeah, so I'll be reminding you, if anything, I'll make something with solutions, maybe something that will contain the tutorial sheet questions with solutions. Yeah, so if I'm going to have time, and then apart from that, we'll also discuss the tutorial sheet just here. We'll be discussing together, putting concepts together and solving the questions. All right, thank you very much for attending tonight's lesson. Make sure that you don't miss the next lesson that we're going to have, where we'll at least apply some calculus to derive certain formulas. And then, okay. All right. Okay, see you next time we're going to see you for mathematics tomorrow.